So today we're going to keep rolling along with probability. You guys are going to be working with the people you're sitting around today. We are going to still bring things together and discuss together as a group for some of the pieces. I want to do something a little different other than, I know yesterday was you doing a lot of listening to me. So I want to make sure you guys get a chance to do some different things besides listen to me lecture. But again, we will do some things together as a group here. So for the first piece, we do need to gather some data from our class. It says some people have shoes of many different colors, while others prefer one color, and so have all their shoes in just that color. So as a class, we're going to complete the following two tables. So take a look at the shoes you have on today. The shoes you have on today. If your shoes are kind of a multicolor thing, pick the color that takes up most of the shoe. Okay? All right, so raise your hand for me. So you can only vote one time. You can only vote one time. Raise your hand for me if you're wearing blue shoes today. Any blues? Any blues? No. So that is that's a 0. Okay. All right, raise your hand if you have black shoes today. 1, 2, 3, 4, 5, 6, 7. All right, 7. Oh, where'd it go? What the heck?
Oh, no. Hiding. No.
Blue 0. And black was how many? What did I say? 7. Okay, now maybe I'll stay. Raise your hand if you're wearing white shoes today. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so 9 people with white. Brown or tan? Anybody have brown or tan on today? Nobody? Okay. How about red shoes? Anybody wearing red today? No reds. Wow, this is not a very diverse group of shoes in here. Raise your hand if you have some other color. 1, 2, 3, 4, 5 people have some other color. Okay, so now our other task is you have to think about and get as close as you can. I know for some of you are like, Miss Guy, I have a walk-in closet just loaded with shoes. Yeah. And others of you are like, Miss Guy, the shoes I'm wearing today, I have these and I have a pair in my gym locker and that's all I got. So, to the best of your knowledge, how many of you own blue shoes? Not how many pairs of blue shoes you own, but raise your hand if you own blue shoes. There's a pair in your closet that's blue. 5, 6. Okay, 6 people. Again, this is what you own. Raise your hand. I'm going to make this easier. Raise your hand if you do not own black shoes. Okay. And I think we've got 21, it looks like, from our last little survey. Okay. Raise your hand if you do not own white shoes. If you do not own them. 2, 3. I don't know. 4.
No, I think we're done. There's a pair of white Vans. You got white Vans? No, she doesn't have white Vans. Oh.
So 5 people don't. So 16 people do. I know black and white are usually the popular ones when I do this, so that's why it's easier to do the not piece. Raise your hand. Oh, brown's always a tough one. Raise your hand if you own brown shoes. Raise your hand if you own brown ones. This one's always hit or miss for me. 6, 7, 8, 18. Okay, that would have been easier to do a not one on that one too. All right, raise your hand if you own red. All right, we've got 9. Okay, so look at all the colors we have listed there. Raise your hand if you own some other color. If you own some other color than the ones that are up here. Okay, everybody owns some other color. Holy cow, this class has a lot of shoes. Okay, so we're going to use our data to start discovering some probability rules. We talked about a lot of the basics yesterday. So before we continue on, I just want us to read the little blurb right below these tables. It says, in mathematics, the word or means one or the other or both. So the event that a student owns white shoes or black shoes includes all the following outcomes. The student owns white shoes but doesn't own black. The student owns black shoes but doesn't own white. The student owns both white and black. So all of those cases would have to be considered if we're looking at students that own white or black shoes. So I always have to wait to fill in the pieces till I get my data. So let's do man, nobody's wearing. Let's do white's okay. Okay, we'll have to just do. We can do black and white because other's not going to work either. Okay, so let's go. So what I want you to talk about with the people you're sitting with, talk about parts A through C on the front side of this sheet. See what you can come up with. Put your heads together, talk about it, see how you would answer those questions. And we will bring it back together and talk about it once we've all had a chance to try it out. So talk about the people around you, see what you can come up with for the first part here, the A through C on the front side of this sheet. See what you can come up with, and we'll bring it. So if you read through, it says, in part A, it says, which question can you answer using the data in the tables? And answer that question. Which one of those two can we answer? Part 1 or 2? Part 1. What's the answer to part 1? 16 out of 21. Now, some of us were saying, like, Miss Callie, why can't I answer part 2? Some people answered part 2, and they said we had 37 out of something. Somebody that answered part 2, what did you get? What's wrong with that answer? Yeah, you're counted more than once. How many people are in this class that took this survey? 21. So if I'm finding a probability with something to do with this class, what's my total going to be out of? 21. So if I want to know if a student owns black or white shoes, I can't have a probability out of 91 when it's a class of 21. So I don't know who said it, but they're on the absolute right track. People are double counted. Some of you are triple and quadruple counted because you had multiple colors of shoes. So we have to figure out how to take care of that. So why can't the other question be answered? Well, right now, I like the response. People are double counted. People are double counted, or triple or quadruple, whatever you want to put. People are counted multiple times. Our total right now is sitting at 91, but there's only 21 people in our class. So what information do we need? How do we get rid of those people that are double counted, once for black and once for white? What do we need to know? We know the students that own white shoes. We know the students that own black shoes. What don't we know? What didn't we ask? How many own both? So that keyword or means these three situations. So we have to think about the people that own both, because those people that own both are counted once because they own black shoes, and then they're counted again because they own white shoes. So they're double counted in both categories. So the people that own black shoes was everybody. 21 out of 21 people own black shoes. And then if we add into that, how many people owned white shoes? 16 that owned white shoes. We get too many. Holy smokes, we've got 37 out of 21. We talked yesterday, probabilities can't be bigger than 1. Because people are double counted. People are double counted. So I know based on our data, we didn't have a very good variety for our colors that people were wearing today. So how many people, if we look at this, how many people are actually double counted? 16 of them are, right? Because everybody owns black shoes. So the 16 people that also own white, they're double counted. They're counted once here because they own black, and they're counted again because they own the white shoes. So we have to subtract out, this is own white, this is own both. So in our class, to own one or the other, that is 100% happening in here. Because everybody owns black shoes. So I know this one didn't work out as well as I'd hoped because we didn't have enough variety on what we're wearing today. Maybe I do need to throw gray shoes in there. That'd be a really good suggestion. But the idea is we have people that own black shoes. We have people that own white shoes. They're double counted if they own both. So we have to subtract out those double counts. That's what we have to be careful of when now we start building on that, on those basics from yesterday. So sometimes my shoe example doesn't work out the best with using data from you guys. So I always have a backup. Flip to the back of this sheet. I always have a backup in case it doesn't work out the best. Or if it does work out, this helps hit home what we need. I found this Minnesota student survey asking teens questions about school activities and health. This was a 9th grader survey. And it says, how many students in your school are friendly? So the numbers of boys and girls who gave each answer are shown below. It says, suppose you pick one of these students at random. What I want you to try for me, let's try out, so we can kind of check as we go. Please try out for me A through D, you and your partner. Those should be straightforward from the work we did yesterday with the basics. So try out A through D. After you guys get started, I'll start putting some answers up here. Put that up here so you've got it. The grand total should be 49,210. It does give it to you in that bottom corner, but sometimes I get people that they start adding a whole bunch of things up. I don't want you wasting that time. The grand total is there for you. So again, just try parts A through D. I'll start gradually putting them up as you're working so you can check as you go. And then we're going to kind of take it to that next level and hit home that idea of our addition. Yep, go ahead, guys. Leave these as fractions, please. Just so we can see our rule a little easier and work with them a little easier. Just leave them as fractions. Just leave them as fractions, totally fine. I know some of these can be simplified, but so we can see our rule today, just leave them out of 49,210. just so we can see our rules today, so they're a little bit more obvious for us. Please check yours with mine. I'm just jotting them down here as I go, making sure my numbers aren't disappearing off my screen, because that's not cool. Also, make sure you're working on that labeling piece. If you're labeling them like I am, it's going to make finding some of those other parts a lot easier. If it's labeled, I don't have to go back and reread part A to know what that probability is representing that I found. If I label, I don't have to go back and read part B for me to know what my answer means. It's labeled. I'm ready for that. All right, so check your top part. This would be a refresher on our empirical probability from yesterday. So given that data, those observations, can you find those first four probabilities? That's a nice little checkpoint for empirical probability from yesterday. Now, for part E, it says think about how you would find the probability that the student said that all students are friendly, or most students are friendly. So you and your partner talk about part E. So you're trying to find, can you find the probability that a student said all, or they said most? Can you get that just from your table? Talk about that with your partner. Now, right away when I asked that question, I heard a lot of people say yes, and then they started working. So how are we finding it? Adding the two together, right? So we're adding together the all, and the all was what, 783 I'm hearing? We're adding together the all and the most. So 27,368. We're adding together the all and the most. If you didn't write it out like this, guys, that's okay. I'm just doing it so you can see where the numbers are coming from. If maybe you didn't grab onto that right away. Some of you, like I said, you just said, yep, and you started working. Awesome. Okay, so that's the probability that all or most. Now, your last task on this side says, think about the probability that the student is a girl or said that all students are friendly. So you're trying to find probability girl or all students are friendly. So can you answer that right from the table? If not, if you can't, then look at part 2. It says, can you find the answer if you also throw in what you found in part D? So something to think about. Think about what we did with the shoes and think about, see if you can transfer it now to this particular data. Talk about it with your partner. So the question is, can I find my probability just using part A and part C? Part A is the probability that a student said all students are friendly, and part C said the probability that they're a girl. So can I just take the probability that they're a girl, add it to the probability they said all are friendly, and be done? What's the problem with doing that? It worked in part E. I just added the all and most together, and we said, yep, looks good, move on. What's wrong with that? How is this different? Because all the girls are counted for the probability of a girl, right? But they're also counted where? There's also some girls that said all students are friendly. So there's some girls being counted once here. All girls are being counted once there. And then there's girls being counted a second time because they responded that all students are friendly. So I can't do it with that. I need to think about those girls that are double counted. So what I need to do to accomplish this is I'm going to need to take the probability that they're a girl plus the probability they said all students are friendly. But then what do I need to get rid of? Yeah, we need to get rid of the girl and said that all are friendly. So minus the probability of girl and all. So this was part C, this was part A, and then this was part D. Those are the different parts. I have to think about those things that might be double counted. I realize in this one, if you just added together the girls plus the all, you didn't go over the total like we did with our shoes. But just because you don't go over one doesn't mean something wasn't double counted in there. We have to be careful with that. So if we do that piece, I had a total on that. If you do those things, we do our add and subtract, we get, oh, and mine cut off on here, hang on. All right, so we should get 25,691 over our 49,210. So we have to think about those things that could be double counted. We have to think about those things that could be double counted. In part E, you can't be counted twice there. You either responded that all students are friendly or you responded most are. There's no overlap there. There's no double up. But when we move to something different where we have that they are a girl or they said all students are friendly, there's girls that fall into both counts there. There's girls that fall into both, so they're double counted. So if you go to your next sheet, I really want to focus in on this idea. Two events are said to be mutually exclusive if it's impossible for both of them to occur on the same outcome. So with our student data, it was impossible for somebody to answer all and most on the same survey. I could not get a student survey that said all and most on it. Those two things are mutually exclusive. Now I could get a student survey that was filled out by a girl and she said all students were friendly. So those two things are not. So for example, letter A, you roll a sum of 7 with a pair of dice. You get doubles on the same roll. Can I roll a 7 and also get doubles on the same roll? No, I can't. So those two things are mutually exclusive. We wouldn't have to worry about things being double counted. They can't be. Letter B, you roll a sum of 8 with a pair of dice and you get doubles on the same roll. Can we do that? That can happen. So here's where our brain has to think a little different. Those two can happen at the same time, so they're not mutually exclusive. So talk about the last few with your partner and decide which things are mutually exclusive, and we wouldn't have to worry about double counts, and which things are not mutually exclusive, and we'd have to worry about double counts. Talk about it with your partners. Take a look at those. All right, so let's see what we think. And if you and your partner debated, hey, you get to see who's right, have bragging rights for a little bit here today. All right, so letter C, it says Isaac wears tennis shoes today to math. Isaac wears dress shoes today to math. All right, so we said that Isaac cannot do both of those things at the same time. So that is mutually exclusive. I know it's different for our brain to think about that those things can't happen, so we're saying yes, it is. I know it's a little tough to think that way. All right, Sarah owns white shoes. Sarah owns black shoes. They're not. Drawing a queen from a deck of cards, and the card is also a heart. Not. All right. Drawing a club, and the card is also a diamond. Those are. I can't get a card that's both. Selecting a male student from an assembly, and that student's also a senior. Those are not. Okay, so let's summarize up here the difference between the two and how we handle them with the probabilities. We've seen both types today. So now let's see how we handle those and what we do when we do a probability with them. So it says, suppose two events are mutually exclusive. Which of the diagrams below would actually represent the situation if they're mutually exclusive? Would they overlap or not? What do you think? If they are mutually exclusive, do they have anything in common? No. So that second diagram is going to best represent our situation. So in part B, it says, what does the fact that A and B are mutually exclusive mean about the probability of A and B? So what would happen? Can A and B both happen at the same outcome? If they're mutually exclusive, can they happen on the same outcome? No. So the probability that they both happen on the same outcome has to be 0. Cannot happen, will not happen. So if they're mutually exclusive, how can you find the probability that A or B happens? What did we do when they were mutually exclusive? What did we do when the students responded all or most? They were mutually exclusive. What did we do with the probabilities? We just added them together. That's all we did. So if two things were mutually exclusive, we just added their probabilities together. So probability A or B, all we had to do, sorry, my 0 and stuff moved, guys. I don't know why that's doing that today on me. Is add together the probability of A with the probability of B. And that's it. If things are mutually exclusive, nothing is double counted. Those events cannot happen at the same time. So it's like a student wearing, we had our shoe example, when we had students actually wearing today black shoes or white shoes. Those two things were mutually exclusive because you chose one or the other. Even if your shoes had both colors, you chose one or the other for our survey. We just added them together, that's it. Now if, come on, scroll. Now if they're not mutually exclusive, what does that look like on our Venn diagram? They're going to overlap. They're going to have the possibility of both things happening on the same outcome. There's going to be that overlap. There's going to be those double counts. So, it says, what does the fact that A and B are not mutually exclusive mean about the probability that they both can happen on the same outcome? Where's the probability on the diagram that we chose? So if they're going to both happen at the same time, where's that located on our diagram? It's going to happen right in that middle part. A and B happening at the same time is that middle piece. So if we wanted the probability of A and B, it's going to be something other than 0. It can happen, it will happen. So we have to take it into account. It's like on our survey, our student survey we had, where they were a girl and they responded that all students are friendly. All right, so we have to think about those double counts. So if we want the probability of A or B, and they are not mutually exclusive, we still add the two together. But then what do we need to take out? Yeah, when they both happen. Those double counts, when they both happen. So the probability of A and B happening at the same time. So today it's all about addition, and I know that was pretty obvious for us. A lot of you were choosing addition when I asked you just to try some of the questions, but there's two different rules. So you have to stop and ask yourself, are they mutually exclusive and all I have to do is add and I move on in life? Or are they not mutually exclusive and I have to worry about subtracting out the things that are double counted? That's what you have to think about. to finish up today, there's just a few problems in part 6 I want you to try out. And then tomorrow we'll have a work day for anything from 4-1, and there is a 4-2 assignment at the bottom. You might want to, this talks about rolling 2 dice and a deck of cards. So you might want to look at page 187 in your textbook. I'm going to go ahead and put the answers up here, and then you can check as you go and ask me whatever questions you need. Oops. Probability doubles. Again, I'm just going to put the answers up here, so if you need, and if you're working with somebody else, just maybe one of you has to open to page 187. Oh, let me put the simplified here. It was 10 out of 36. Orange. So again, check yours with mine. I didn't put the work up there, so let me know what I can help you figure out.